All right, hello everyone. Welcome to our Unit 2 lesson, lessons number 8 and 9 on end behavior. In this unit, we're going to look at how the functions that we've been studying, these polynomials, tend as they go away from the x-intercepts. So you might remember the idea of a parabola. And if you recall, a parabola is a U-shaped graph that looks a little something like this. I just sketch a quick graph here in my blank space. And it looks like a U shape. It has a vertex. This one, the vertex is a minimum. And the two ends appear to go upwards. But where do those two ends go? That study is called end behavior. And what we understand is that for a parabola, those lines are going to go up forever because, especially as x increases, y will increase. And like if you were to take a function like y equals, say this is x squared, minus 5. Okay? The higher x gets, then the higher y gets, which is why the function goes up and up and up and up. So this is going to be a generalization unit for um, this sort of behavior and how it works for all functions, not just quadratics. Okay. In particular, one of the major things that we're going to look at is the idea of an even degree and an odd degree. Um, so remember what degree means. Degree is that highest exponent of the polynomial that gives us most of the properties that it has. But ultimately, our goal at the end of this is to look at those functions and identify what the ends of the graph are going to do, not just based on the graph, but also simply based on the equation. All right, let's get started. All right, you may have remembered this from class if you were in class seeing this. We did a little Jamboard activity with this. So we have two functions. And in particular, we notice something about the graphs, or maybe you have a question about these graphs. Like, for example, um, I notice that this first graph, notice the y-axis goes all the way to 8,000. Is it necessary for the graph to go to 8,000? Um, Certainly as x goes to 20, perhaps so. 20 times 20 times 20, might be a number much, at or much higher than 8,000. Like if I were to do 20 to the third plus 4, times 20 squared minus 20 minus 4, I'm going to get a very, very large number. I'm going to get a number, let's see, this is 8,000. 20 squared is 400, and 400 times 4 is 1,600. So that's 9,600. So it's minus that, so it's going to be 9,500 and something. So it is a very, very large number. And, you know, one thing that I noticed about that is that's interesting why they would choose that. Um, does the graph have to be so big in order to draw this graph? And I also might wonder if I look down here at this x-axis, right? Like, how many times is it really crossing the x-axis? Same thing with the graph over here. No, first thing I wonder is it kind of looks like a parabola, but it's not. The graph is kind of bent, like it's got a vertex, but kind of like not really. It's just kind of squished in a little bit. And I noticed that, and I noticed that the degree is 4, and I wonder, is that, a symptom of the fact that it's got an x to the fourth? It's a degree of 4. Okay, so I also might wonder, like, how many times is that really crossing the x-axis, if at all? Because again, the scale goes to 8,000. So these numbers, like each line is worth 2,000. So who knows what's happening here? Um, just as a side note here for this, not really as pertinent to this lesson, but one thing that we could do to figure that out is to factor these expressions. So for example, this first one, right? You might remember this first one is a factor by grouping problem. If you remember from last unit, we did some factoring problems like this. And it turns out that this factors into, let's see, x squared, x plus 4, minus 1, x plus 4. So x squared minus 1 times x plus 4. It's okay if you don't quite remember that from last unit, but that is certainly something that we did. And I know I quickly went through that, but that is something from last unit and is not, it's just more of an extra here. And this factors x minus 1 times x plus 1. Remember, that's a difference of squares times x plus 4. So it turns out this, from our last lesson, this crosses the x-axis 3 times. It's going to cross at 1. It's going to cross at -1, and it's also going to cross at -4. Now, those numbers are hidden here because of the scale of the x-axis. This one does something very similar. We have not actually factored problems like this, but it turns out it does factor. It turns out it factors into x squared minus 9 times x squared minus 1. -9 plus -1 is -10, and -9 times -1 is +9. But why the x squared? And it turns out the reason why it's x squared is because the functions here happen to be even. Again, the factoring part is not like something that we're really working with right now, but is one way that we can analyze what's going on in this function, right? And again, these are difference of squares, x minus 3, x plus 3, x minus 1, and x plus 1. So it turns out this will cross the x-axis 4 times. So that's really kind of a technical side note. So it is actually crossing the x-axis 4 times, but we can't see it because of the scale. So then we wonder, look at the difference between these two, okay? Notice how the x to the third graph, it's got one end pointed up, one end pointed down. But this x to the fourth graph has both ends pointed up. So we wonder, is there a difference? Why is there a difference? Okay, so we did a Jamboard in class. We won't necessarily fill this out here. The Jamboard had a little bit of the notices and wonderings from the previous slide. And then we had this. So in order to kind of save time a little bit on the video, this is the result of one of the activities that we did. So there are 4 polynomials, x squared plus 1, x to the third plus 1, x to the fourth plus 1, and x to the fifth plus 1. And here are some different values of x that you can plug in into the function. So for example, if I take -1000 and square it and add 1, this is what I get. If I take -100 and square it and add 1, this is what I get, and so on and so forth. Okay, so what do you notice? You might notice this. Notice that some of the numbers are negative. And you might notice for x squared and x to the fourth, despite having some x values that are negative, the answers are always positive. Do you know why? It's because of when you square something, right? When you square something, you're taking a number and you're multiplying it by itself. So you take a negative, negative times negative is equal to positive. And so you might remember that with x squared, these are all going to be positive because no matter what, you're always going to have a negative times a negative or a positive times a positive, and those will always be positive numbers. So then when you add 1, your answers will necessarily all be positive. What happens when you have a third power? So with a third power, we can plug these numbers in, but this time they end up negative. Why? It's because, and I'll again, I don't have a lot of room to write this here, but negative times negative times negative. So remember, the third power means you multiply something by itself, right? So you have, say, negative 10. Negative 10 times negative 10, that's going to be a positive. So this is equal, the first two negatives will multiply together, and you'll get a positive. You'll then multiply it, bring down the next negative, and a positive times a negative is a negative. So when you have three negatives, these values are negative. What about an x to the fourth function? Now, x to the fourth, now you have four negatives, right? So now you have, now let's erase this. Can I erase my mark here? There we go. I'm going to erase this here. So what happens when I have x to the fourth? So now I've got negative times negative times negative times negative. Well, the first two make a positive. The second two also make positive, and positive times positive is positive. So that's why all of these end up positive. X to the fifth, you kind of see the pattern going on here, right? We have an odd number of negatives. Here, we have an odd number of negatives. And that's important. Here, we have an even number of negatives. And here, we have an even number of negatives, which also matches the degree. This is second degree, third degree, fourth degree, fifth degree. So now let's think about this, right? We're going to describe some of the similarities and differences between the polynomials, right? So it looks like the main thing that's happening is odd and even. If you have a degree that's even, it looks like the numbers are all staying positive. But if you have a degree that's odd, it looks like some of the numbers are even. It keeps the sign. Some are positive, but negative inputs lead to negative answers. Interesting. So let's see if we can think about this. So, odd degree, positive and negative answers. Even degree equals all positive answers. So do you think that would continue? Sixth power, seventh power, eighth power. So would a function of x to the 13th, would you get negatives from negatives? Sure. Okay. How would the end behavior of the polynomials change if there was another term like 100x? Okay, here's an interesting situation. So what if we added a new term into this? Let's say we take one of these, right? We'll take the first couple, x squared and x to the third, right? And let's say we add a middle term. So let's do this down here. So let's say we had x to the third, or sorry, let me back that one up a bit. We have x squared plus 1. And then let's say we have x squared plus 100x plus 1. X to the third plus 1, and x to the third plus 100x plus 1. And let's pick a number to put in. Let's pick in two numbers. Let's plug in, let's do 100, and let's do even negative 10. Okay. All right. So do you remember what some of these were? Okay. So 100 squared is 10,000 plus 1, so that's 10,001. But what's going to change if I add 100x? Okay. If I add 100x, well, that's going to add 100 times 100. That's going to add another 10,000. Now it's 20,001. So that number is still going to be positive. Okay. What if I have this function x to the third plus 1? Okay. Now let's do it. So now we're going to have this is, I believe, 1,000,001. Oops. So still a very positive number, right? And then x to the third plus 100x plus 1. Now we have, let's say, so that's going to be what, 1,000,000. But we're going to add again, we're adding 10,000. So it's 1,010,001. Okay. So when you add the 100x term, they remain positive, right? But what about negative 10? Let's try that. So this is going to be negative 10 squared, so that's 100, and 100 plus 1 is 101. Now in this case, 100x, this is going to be negative, it's going to be negative because now you have negative. So it's negative 1,000, so you're looking at negative 899. Over here, now what's going to happen? Negative 10 to the third power is negative 1,000, plus 1 is negative 999. And then here, you're going to have negative, again, negative 1,000, so negative 999. But this is going to make it go even more negative. So you're going to have negative 1999. Okay. So here's the thing about this. Now, it's not so evident with the negative 10, but look at the 100. Does the 100x term really do a whole lot in this expression? Okay, so for the negative 10, yeah, it does. But look at 100. Look at 100. This is more important, right? So it's going to make a positive number. It makes it just more positive. With x to the third, that 100 to the third power is so big that adding a 100x term doesn't really change it that much. You go from 1,000,001 to 1,010,001, which is hardly much of a change at all, comparatively speaking. Here, it just makes it more negative. Here, you do go from positive to negative at the x squared level. Yes, but in this case, 100, the 100x does, in this case, outweigh the x squared. But what happens if you did a number like 1,000,000? At that point, the million squared is going to far outweigh the 100x. So how would the end behavior change of the polynomials if there was another term like 100x? Ultimately, it won't. And the reason for it is that exponent term, as we said before, dominates the discussion of all the properties of the function because when you square larger and larger numbers, they're going to be the largest numbers in the problem, no matter what. And we talked about that during the last unit. Okay, let's continue. All right, so here is some of the kind of summary from what we just did. All right, so as x gets larger, and larger in the negative direction, y gets larger and larger in the negative direction. And the reason for it is because when you cube, or third power, of a negative number, you get very large negatives. So how it happens here, as x, so let's write it out, right? As x gets larger in negative direction, y gets larger in what direction? Positive direction. And the reason for that is what we described before. We said that the goes up and up and up because a fourth power of a negative number is positive. And the fourth power of a positive number is also positive. So both ends of the graph are going to be pointed upward. So as x gets larger in the positive direction, y also gets larger in the positive direction. Okay. All right. So now, can we say what's going to happen now about this function? So state the degree and end behavior of the following polynomial function. Okay, so what does this all mean now? What is the degree of this? Is it 3? Nope. It's 4. 2x to the fourth. This is a degree 4. Because it's a degree 4, that term is going to override all other terms when x is very large. So like if x was a million, a million to the fourth power is way larger than a million to the third power. So therefore, what will happen is this term dominates the discussion. And what happens when you take numbers raised into the fourth power? They will always be positive. So as x gets larger in the negative direction, in other words, what's going to happen if you have numbers like negative 1,000, negative 10,000, and you plug them in? What's going to happen? You're going to ultimately get a positive number. These numbers, yes, this will be negative, but it won't be big enough to overtake the fact that these here will be positive. Y gets larger in positive direction. Okay? And then the sister statement to that is what happens in the positive. And as you can imagine, positive numbers, this is all going to be positive, right? So as x gets larger in positive direction, y gets larger in positive direction. There you go. And so that's the big idea. If you have a even exponents, an even degree, both ends are going to either point up or possibly point down. What would make the graph point down if you have an even degree? If this were negative, maybe. Then they'll either be both positive or both negative. So even degree, you're going to have a function that either does this or does this. But if you have a function with an odd degree, you're going to have a function that does this or does this. That's the big idea. Okay. And so here's the idea. The x squared next to the fourth, both ends point up, but x to the third, the ends point in different directions. The same would hold true for x to the fifth, x to the seventh. It would point in different directions. Okay. So here's another idea. Okay, as we said before, and just really kind of a chart showing the result of what happens. So if you take this function, you have x to the fourth minus 30x to the third minus 20x squared plus 1,000. So for certain values of x, yes, x to the fourth is smaller than the other terms. In fact, if you look at, say, number like 10, right? And if you plug 10 in for x, yeah, look at what happens. If you look at 10, you plug 10 in for x, yeah, the biggest term is the negative 30x to the third. That dominates there. But guess what happens when x gets very, very large? Say negative 500 or positive 500. You're going to raise to the fourth power this 500, this negative 500, and guess what? It makes up the bulk of that polynomial. So when you look at all four of the terms that are in that polynomial, this is massive, and the majority of it is the x to the fourth term, whether you look at it here or whether you look at it down here. So even though you have some negative numbers here, like negative 20x squared is a negative number, the fact that it's only negative 5 million means it's not going to affect the end value so much. Same thing down here. If you look at 500, yes, those are negative, doesn't matter. X to the fourth is so huge that it's what dominates the discussion. That's why when we look at end behavior, we only care about the leading term. We don't need to worry about what's happening with the rest of them. Okay, and that takes care of the first part. Okay, so now we can jump on to the second day. So I'll make sure that there's a chapter break here on my YouTube video. So here we're looking at going a little bit deeper into end behavior. Okay, so can we match each graph with the function that it represents? Now, here's the thing about this particular graph, right? Again, we're not going to care so much about the x-intercept. In fact, I don't even have the scale. All I care about is what's happening with the ends. And that's why the A, B, C, and D are covering the center of the graph so that all you're looking at is just the points. So, question, which of these equations is going to have which type of end behavior? Could you figure it out? Take a second. You could always pause the video if you'd like to figure it out for yourself. Okay, so let's look at each of these, right? So remember that in order to get certain combinations, that we need very particular results. Okay, so for example, for part graph A, in order for the ends to open up on both sides, what must you know? You know that you would need, in order to get it to, remember what kind of function would have positive on both sides? You would need an even degree. These two, because one end points up, one points down, one points down, one points up. These ones you would need an odd degree. And then what about B? It's flat. Well, if it's flat, it means it's linear. But not only linear, it's got a slope of 0. So this is a constant line because this line has a degree of 0 because it has no slope, or a slope of 0. So there's no x value to make the graph rise. Okay, so which graph is which? So let's see, y equals x times x plus 3 times 2 minus x. Okay, so I guess the question is, oh, it's in factored form, right? So how do you find the degree? Well, let's figure out what that leading coefficient is, right? So remember, when you multiply this out, you're going to get that leading coefficient from all the x terms, right? So if you were to distribute this out, the easiest way to do it is to distribute all the x terms. So x, now you have an x here, so x times negative x, and you're going to get a negative x to the third. So it's an odd degree. Now, it's an odd degree, but now here's the thing. Now, it's an odd degree, but these two are both odd degrees. So which is it going to be? Is it going to be C or is it going to be D? Well, let's think about this. So we didn't actually discuss what happens with the negative, right? And the fact that these could point out two different directions. What might cause the graph to open one way versus another? Okay, the only way to find out is to maybe try plugging in some big number, right? So remember, what we said last unit was that end behavior is really determined with very large x's. So let's say we did like 1,000. So what is negative 1,000, parentheses, negative 1,000 to the third power? Notice this minus sign is outside the x to the third. So 1,000 to the third power, well, that's a big number, right? But is it positive or is it negative? Okay, so this is going to be, it looks like that this number, when I plugged in positive 1,000, it's going to be a big number, but then it's made negative. So a positive 1,000 leads to a negative answer. And you can prove that by plugging in 1,000 even into this function. You get 1,000 times 1,003. Okay, that's still positive, times negative 998. And so your answer is going to be negative. So positive x, negative y, which is it? Is it C or is it D? It's going to be C, because a positive 1,000 is going to lead you to a negative answer. Okay. So do you think then that this might be true anytime your leading coefficient is negative? Could it be, if that term is negative, that the graph is shaped like that? Possibly so. Okay, 2. It's degree 4, right? We got a 5x to the fourth, easy enough. There's only one that's an even degree, and that's A. And now think about it. It's positive, positive 5. Positive result multiplied by positive 5 means the ends are going to be positive. Okay, that matches. What about this one? 5x plus 3 minus 5x. Well, if I distribute that, I get 5x plus 15 minus 5x, which is just 15. And that's just a constant, so that must be B. Interesting. Okay. So now let's use our knowledge from the last lesson and see if we can put a few things together here. Write an equation for a polynomial with the following properties. It has even degree, has at least two terms, and has the inputs get larger and larger in either negative or positive directions. The output gets larger and larger in the negative direction. Okay. So even degree. So even degree, we could do x squared, x to the fourth, x to the sixth. Doesn't matter. Let's do y equals x. I mean, we can even do something simple like x squared, right? Now, what does x squared look like? Now, x squared is a graph. Oops, looks like a parabola, right? Kind of drew that a little bit funky. It's supposed to start at 0, 0. Let's fix that again. There we go. So here's my problem. Now, in this particular case, the outputs get larger and larger in the positive direction, right? How could I get those positive values to turn negative? You make them negative, right? You multiply by -1. So what I'm going to do is I'm going to take this graph and I'm going to put a negative sign in front of it like that. And when I make that negative, guess what happens? It flips the parabola upside down. And we already knew this from our work from last unit, is that parabolas that have a negative x squared term, they face downward. Do you think that would happen with x to the fourth, x to the sixth? Sure would. And then all we need is to add another term to this. So it has at least two terms. Does it really matter? The answer is no. As long as you don't create a higher degree polynomial, I can add another term here. I can add 3x, 5x, 10x. It doesn't matter. No matter what I do, this parabola will always be pointed downwards. Um, so just for simplicity's sake, I can subtract 3. And what does that do? All that does is it's going to take this parabola and shift it down 3 units. So now we have this. I know, clever use of ink, huh? So x squared, negative x squared, minus 3. Okay, so that's an example. But I could even do y equals negative 2x to the fourth plus x to the third. And it turns out that will still do the same thing. Why? Because with a very large x, if I have a large number raised to the fourth power, that's just going to be big, right? Big and positive. But then as soon as I multiply it by a negative, it's going to turn negative. And then this won't be able to overtake it because x to the third is much smaller than x to the fourth for large values. So this works as well. Okay, write an equation for a polynomial, odd degree, has two terms. As the inputs get larger and larger in the negative, direction, the outputs get larger and larger in the positive direction. So negative input, positive output. And as the inputs get larger in the positive input, negative output. Well, hey, didn't we already have a function to kind of match that? So negative input, positive output, and it's got to have an odd degree. So first odd degree, x to the third, right? So if I had y equals x to the third, well, what do we know about that? If I square a positive, I get positive. If I square a negative, I get a negative. But what happens if I put a negative in front of it, like this? Now what I get is if I plug in, say, like, 100. So negative 100 to the third power, that's going to be 1 million, but the negative is going to make it negative. So positive goes to negative. And what if I did this? Now all of a sudden, negative, I'm going to get negative to the third power, so that's going to be a negative. So I'm going to get negative 1 million. But then this other negative is going to be outside of it, and it's going to cancel with this negative, and it's going to be a positive 1 million. Another way to think about it is this is now creating, you've got 3 negative signs, and then this negative makes it a fourth, and 4 negative signs turn positive. So guess what? A negative x to the third will work. And then just like before, we can just slap another term on here. Doesn't necessarily matter what it is. I could do 2x squared. It doesn't matter because this is far smaller for large numbers than x to the third. And so again here, almost anything. And by almost anything, I mean as long as it's the term has a lower exponent than 3. Okay, so let's describe the end behavior, right? All right, so which is greater? Okay, end behavior. So let's look at M. Now, rather than write the whole sentence out, let's at least think about it, right? So what's happening with M? It's got a negative x to the third. Remember, it's dominated by that first term. So what's going to happen? So positive input, what's going to happen? Say you put like 1,000,000 in for that. It's going to turn negative, and those don't matter anymore. Negative output. Is the reverse true? Negative input, negative raised to the third power is going to be negative, and the fourth negative sign makes it positive. Okay. What about for n? Positive input, negative input. So the positive input, what's going to happen? Again, you're going to get, when you square something, will always be positive, whether positive or negative, doesn't matter. But then what's going to happen? Say you put like 1,000,000 or negative 1,000,000. It's going to turn into positive, like 1,000,000,000,000. And then this is going to make it negative 20,000,000,000,000, no matter what these are doing. So both positive input, negative output. Which function has greater values for x being greater than 0? Well, that's going to depend, right? So, in particular, um, as long the thing here is the difference between these two terms, x to the third and x squared, and this is a negative 20x squared, and that's negative. So, really, you've got this extra factor of 20. So, this third x has to take the place of this 20. So, as long as x is larger than 20, x to the third is going to be bigger. Now, that's just kind of an estimation, and you may have to fine tune that based on the results of these, right? But in general, M is larger when x seems to be greater than or equal to approximately 20. Actually, it may even just be greater than 20 because it looks like even at 20, n is going to be bigger. m is larger when x is greater than 20. Would the same hold true for negative? Well, the negative is a little bit different, right? Um, because again, with that negative sign, um, negative input is going to lead to a positive output. So m is going to be bigger, definitely with negatives as well. It seems pretty clear then that m is going to be larger when x is negative. Maybe not right away, but most x numbers. And we only know that because, again, we have the end behavior up here because um, m will give you positive values when the input is negative, but n will not. Okay, so now what we're going to do is we're actually now going to turn this into the formal notation. So thankfully, we don't always have to do all that writing. So if you look at the informal notation, as x gets larger and larger in the negative direction, m of x gets larger and larger in the positive direction. That is a mouthful. But guess what? We have a word that references larger and larger. And actually, we have a symbol for numbers that get large and larger and larger and larger. And that symbol is infinity. So we can actually shorten this whole statement by using infinity. So as x goes to infinity, y goes to, um, well, let's see what's happening here. As x goes to infinity, m of x gets larger. In other words, the output gets larger in the positive direction. As x gets larger in the positive direction, negative infinity. So in other words, negative infinity means large negative values. So for m, as x gets to big positives, the output becomes big negative. And vice versa is true. As x is large negative numbers, then that function ends up being positive. What about for n? In both cases for n, as x approaches negative infinity, in other words, with large negative numbers, what's going to happen? Again, positive times negative, y approaches negative infinity. You get negatives. As x approaches positive infinity, y approaches also negative infinity. And that was from the talk we had before that with an even degree, but has a negative coefficient, those values are all going to be automatically very large negatives. So this is now the shortcut that states all of this. Much simpler, and this is called the formal notation. The arrow means it goes to. So as x goes to negative infinity, as x gets largely negative, y gets largely negative. All right. Okay. So at the end of this is a little game that we can play. We won't do much of this here because at this point, this is really kind of something fun that we did in class, but you can always give it a try, okay? And so we did this by just waving your hands, right? And giving us different functions by using your hands, okay? And the whole idea is your hands become the end behavior of the function. So for example, if you have an x squared function, um, like you know it's a parabola, and if it's a positive x squared, you hold both of your hands up like this guy in the middle is doing. If you have an x to the third function, you're going to hold your hands such that you have the one hand going down. So your left arm is going to go down and your right arm is going to go up because that's the direction of x to the third. Okay? So here's a few ones that we can look at. Okay? So y equals x. Now y equals x is a line, so you can hold your hands in a line. Okay, but now a few other ones. Y equals x to the fourth. Okay, so let's put everything together. What degree is it? 4. That's even. Even means both hands go up or both hands go down. So which is it? Both hands positive, so both hands go up. How about this function? So what's going to happen here? Okay, degree 2, so it's even. Positive coefficient, so it's either both hands go up, both hands go down, and both hands go up. Okay, how about this one? Ooh, what's going on here? Okay, what degree is it? It is degree, oh, looks like a degree 5, right? But guess what? Look at this. You have an x to the fifth term that crosses out with a minus x to the fifth term. It's odd, so it's an even function. They either go up or go down. Which is it? That's not right. Oh, okay. Anyway, because you've got that minus x to the fifth term. Okay, so that one's not right. So let's fix that one a little bit here. Because again, what really is going to happen? It's positive. It's next to the fourth. We can graph this. And in fact, we'll show with this one. Maybe I should have quit while we were ahead. Let's give him a third arm. Okay, what about this one? Okay, what degree is it? Degree 3. You have 3 x's. Okay, is that x going to be positive or is it going to be negative? So you've got positive, 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 but multiplied by negative. So you're going to have a negative 2x to the third term. So what's going to happen with this one is it's going to be a negative. So this is the one where the hands are going to point in different directions because it's odd, but it's going to have the left hand up and the right hand down because the function is going to look something like this. So your function is going to look like this. So therefore, your hands will go like that. How about this one? Negative x to the 50th. Even or odd? Even. So this will be, whoopsie. This will be even. It's negative, so is that both hands up or both hands down? This one is both hands down. This guy's upside down. Hey, it's me. I'm doing a headstand. Look at that. Oh, here's another one. Okay, end behavior game. I don't trust this one. What's going to happen? Oh, hey, look at that. It's a straight line. How do we know it's a straight line? Because these two cancel out, and all you're left with is a 6, and that's a constant. When you have a constant, your hands go straight across. How about this one? X to the 101. Okay, odd. That means one hand up, one hand down. But which is it? Positive. So positive means right hand goes up. Easy way to remember the direction for the odd ones is think of it like a slope. So it's bent, but it kind of follows a positive slope. It follows the same kind of direction as a positive slope would go. It's just bent. Okay. All right. So, without using decimals, can we do this now? What does the notation for this look like? Okay, tell me everything about it. X to the fourth, so it's even, and it's negative. So that means both sides are going to point down. So as x approaches negative infinity, what's going to happen? Y approaches negative infinity. Both ends are going to point down. There we go. And that's really what end behavior is all about. So here is kind of the summary for this, okay? So here we go. We have a even degree that's negative. Both ends point down. Even positive, both ends point up. But what happens when you have an odd degree? This one starts with a negative, so odd negative goes down, kind of follow. It's like it's following a negative slope, but just bent. And then odd positive. There we go. And from that, we can make our statements as to whether x goes to positive infinity, negative infinity, and y goes to positive or negative infinity. Okay. All right. And that's the end. All right. Hope you had a lot of fun here. Good luck and do well. Take care.